This video is an introduction to the project Data Science and Machine Learning Resources for Screen Reader Users. Note that the voice was added for the video and is different from the screen reader's voice in the demo. First of all, let's take a brief look at the content of the landing page, https://github.com/hasaku/ds-and-ml- with screen reader. Overview of this project. In recent years, technologies such as data science and machine learning have been adopted in various fields. In the future, there will be more and more opportunities to learn them from an early stage in various types of school education. On the other hand, in order to acquire and utilize such technologies, it is essential to analyze huge amounts of data using graphs and other tools. In this project, I would like to develop the necessary information and tools for screen reader users to learn these technologies by relying on auditory information rather than visual information, in preparation for the future. At present, I have developed two libraries, a library that notifies users of visual status changes on Google Collaboratory with sound, and an alternative library for plots that allows users to check graph data with sound. I have also prepared tutorials on basic machine learning and advanced deep learning using these libraries. The objective is for screen reader users to be able to run through and understand some typical machine learning tutorials. Eventually, I also hope that people who cannot see or have difficulty seeing will be able to use the tools for other scientific research, and that they will be able to find a high-paying job such as data scientist. As the first library, I will introduce a UI extension library to know the state change on Google Colab by sound, which is difficult to be supplemented by screen reader. From now on, we will explain with the demo screen on the actual Colab. The link to the demo can be found on the project page, and by clicking on it, you can launch a ready tour on Google Colab and try it yourself.
From colab_11y_utils import set_sound_notifications new line set_sound_notifications, left parenthesis right parenthesis.
In this way, the library's effects will take effect for all subsequent runs.
Import time new line print, left parenthesis quotation mark start quotation mark right parenthesis, new line time period, sleep, left parenthesis 3 right parenthesis, new line print, left parenthesis quotation mark finish quotation mark right parenthesis.
This is an example of a program that simply sleeps for 3 seconds. Check the sound of the start and end of execution. When the cell starts to run, it will first beep once immediately. Then, when it finishes running, you will hear 2 beeps. This means that you don't have to move around with a screen reader. Also, if you have applied the optional temp/monkey script, you can use shortcut keys to read out the execution status. Like this.
Running now. To first stop, press Ctrl+M followed by I.
Next example.
Raise.
When an error occurs, it will sound a buzzer like this. The iframe area where the results are displayed is a bit cumbersome to access with a screen reader, so being able to see the results without having to move around is quite important. The progress bar with the TQDM library, which is often used in time-consuming executions, is another challenge in using a screen reader. So, I have made some changes to TQDM so that progress is represented by sound.
From colab_11y_utils import TQDM new line for underscore in TQDM, left parenthesis range, left parenthesis 10 right parenthesis, colon, new line time period, sleep, left parenthesis 1 right parenthesis.
This is an example of a program that repeats a 1-second sleep 10 times and uses TQDM to keep track of its progress. Check out how the sound pan progresses from left to right. Next, I would like to introduce the second library, the Graph Sonification Library, to help people understand the graphs visualizing the data without relying on sight.
APL interactive plot 0, 1, 2, 3, 2, 1, 0 right bracket, right parenthesis. Insertion at end of text.
Executed, then scroll down to the result.
The data is plotted as a series of data, increasing by 1 and decreasing by 1 in the middle. If you have the optional temp/monkey script installed, it will automatically scroll so that the entire graph is displayed after execution. So it should not be that hard to get the mouse cursor on the image.
Enter graph.
By moving the mouse cursor to the left or right, the value of the data corresponding to the position will be converted into a pitch and playback. You can also check the value of the data by clicking on it, without relying on sight. Do you see that the data has an upward pointing shape and the value of the pointed part is 3?
Leave graph. Enter graph. X is 3. Y is 3.
Demonstration how to graph multiple pieces of data together and compare each.
Data 1 equals, left bracket 0, 1, 2, 3, 2, 1, 0 right bracket, new line label 1 equals, left bracket 0 right bracket, star len, left parenthesis data 1 right parenthesis, new line data 2 equals, left bracket 3, 2, 1, 0, 1, 2, 3 right bracket, new line label 2 equals, left bracket 1 right bracket, star len, left parenthesis data 2 right parenthesis, new line APL interactive plot data 1 plus data 2, label equals label 1 plus label 2 right parenthesis.
Executed. Then scroll down to the result.
Label 0 is data aligned like a mountain. Label 1 is valley like data.
Enter label example. Label 0 is selected. Double-click to change.
By double-clicking, you can switch the label to be played. While switching labels, you can check the sound of the graph to compare the data.
Label 1 is selected. Label 0 is selected.
In addition to moving the mouse to interactively check the data, I will also show you how to simply play the data. If you simply want to check time series data, this may be more convenient for you.
APL playable plot 0, 1, 2, 3, 2, 1, 0 right bracket, duration equals 500 right parenthesis.
Minimum value is 0. Maximum value is 3. Line 1.
Multiple data can be played overlaid on each other.
Sin equals NP sin pi range 0, NP period, pi star 2, 0.1 right parenthesis, new line to underscore inverted underscore sin equals NP period, array, left parenthesis, left bracket sin, minus 1 star sin right parenthesis, period, T new line APL playable plot 2 inverted sin, type equals quotation mark overlay quotation mark right parenthesis.
Minimum value is minus 1.0. Maximum value is 1.0. Line 1 is sine sound. Line 2 is pulse sound.
The demo site includes an example of obtaining and graphing COVID-19 patient count trend data or others. Try graphing a variety of data to better understand the data. Let's take a look at some machine learning tutorials that can be run by using the libraries presented in the previous sections. The first one is linear regression, which is often referred to as the most basic machine learning. You can see that the multiple data points scattered on the graph in the model with the slope and intercept obtained by machine learning are roughly in line with each other. First, let's check each data to be trained.
Enter data on best fit line. Label 0 is selected. Double-click to change.
Hover the mouse over the graph from left to right and then back to right to left. Did you see that the value of the data increases steadily? Next, let's check the approximate line by trained linear regression.
Label 1 is selected.
I hope you can now understand how machine learning can fit a straight line to data well. As the second tutorial, I will introduce speech recognition using deep learning, which is the current mainstream of machine learning. In order to train a large amount of data with deep learning, you need sufficient computing resources such as a GPU, but Google Colab is free and easy to use, so feel free to try it out. First, let's check what kind of data is trained.
The 35 audio labels are commands that are said by users, period. The first few files are people saying left double quotation mark backward right double quotation mark period. Waveform underscore first comma, star underscore equals train underscore set, left bracket 0 right bracket, new line IPD audio waveform first numpy, rate equals sample underscore 8 comma, autoplay equals true right parenthesis.
Back.
Let's use a graph to see what kind of characteristics the audio actually has as a time series data.
Def wav2 list, left parenthesis waveform right parenthesis, colon, new line return waveform t numpy ravel list, new line APL interactive plot wave2 list, waveform first, width equals 800 comma, height equals 200 right parenthesis.
Ender graph.
Move the mouse cursor from the left to the right. It seems that the first blank period is long and the last pronunciation section is very short. After checking various data in this way, it is clear that it is necessary to use a model that can adequately represent the changes in the pronunciation section. For this tutorial we will use a convolutional neural network to process the raw audio data. CNN can be used to accurately process the raw data. The specific architecture is modeled after the M5 network architecture. After the training process is complete, let's also check the learning curve to see if it is accurate for the unknown validation dataset.
Minimum value is 0.00095. Maximum value is 0.00393. Train loss is sine sound. Validation loss is pulse sound.
As the number of training epochs progresses, you can see that the errors of both training and validation data decrease sufficiently. Thank you very much for taking the time to watch this video. I hope you will visit the project page to try things out and give me a variety of feedback so that I can continue to develop the project in the future.